CANTOR'S Math Integral Calculus Part 1 Video number 21. 5.1. We are going to recollect all the methods discussed in Unit 1 using inverse process. Inverse process means integration is the inverse process or reverse process of differentiation. That is, with the formulae in differential calculus, we have evaluated all these integrals. 1.1. Integrals of the form integral x power n dx n not equal to minus 1, integral 1 by x dx, and their general forms integral ax plus b whole power n dx and integral 1 by ax plus b dx. That is, we have evaluated these algebraic expressions and using this inverse process. 1.2. Integrals of the form e power, that is exponential functions, integral e power x dx, integral a power x dx, and its general form integral e power ax plus b dx. Say next 1.3. we have integrated integrals of the form integral sin x cos x. Say the beauty is there are 6 ratios in trigonometry: sin, cos, tan, cosecant, secant, cot. But here at this stage only we have evaluated integral sin x and cos x, because in differentiation we have the formula: if you differentiate sin x you will get cos x. Therefore, the reverse process, you integrate cos x you will get sin x, and if you differentiate cos x you will get minus sin x. Therefore, reverse process, if you integrate sin x you will get minus cos x. The remaining 4 ratios we will discuss it later. Next, and integral sin x dx, integral cos x dx, and we have evaluated their general forms. 1.4. we similarly here there are 6 ratios with the squares, trigonometric ratios. Among them we have now formula in differentiation, that is secant squared x. If you differentiate tan x you will get secant squared x. Reverse process, you integrate secant squared x you will get tan x. Similarly, if you differentiate cot x you will get minus cosecant squared x. Then the reverse process, if you integrate cosecant squared x you will get minus cot x, and these two only. We will discuss the remaining later and their general forms. 1.5. Integral secant x tan x dx. We know that if you differentiate secant x we will get secant x tan x. Reverse process, if you integrate secant x tan x you will get secant x. Similarly, integral cosecant x cot x and their general forms. And in 1.6, if you differentiate sin inverse x you will get 1 by root of 1 minus x squared. The reverse process, if you integrate 1 by root of 1 minus x squared you will get sin inverse x and its general form. Again, integral 1 by 1 plus x squared dx, its general form, and the last integral 1 by x into root of x squared minus dx and its general form. Try to remember and recollect all these methods of integration on your powerful screen using screen method several times. Then integration will become easier and interesting to you. If you follow these practices regularly, definitely integration will follow you soon. Thank you. We have already recollected all the methods discussed in Unit 1 previously. Now we are going to recollect all the methods discussed in Unit 2. If functions cannot be integrated directly as in Unit 1, certain functions can be integrated after making some adjustment. We are going to discuss these adjustments, that is methods available. 2.1. Some functions can be split and into sum and difference of 2 or more functions, and then they easily integrated. Say, very careful, product and quotient rules discussed in differential calculus are not permitted in integral calculus. Say, come next 2.2, we have discussed 3 shortcut methods, f1, f2, f3, that is integral f dash of x by f of x dx equal to log f of x plus c. Number 2, integral f dash of x by square root of f of x in the denominator dx equal to 2 into root of f of x dx, f of x plus c. Number 3, integral f of x whole power n into f dash of x dx equal to f of x whole power n plus 1 by n plus 1, where n not equal to minus 1. That's 3 shortcut methods we have discussed in 2.2 section. And 2.3, we have already left 4 integrals, that is integral tan x, integral cot x, integral secant x, and integral cosecant x dx. All these 4 integrals they are discussed here in this 2.3. Next 2.41, similarly integral sin squared x dx, cos squared x dx, tan squared x dx, cot squared x dx, these integrals were evaluated, and in addition to this integral sin power 4x dx we have, and integral cos power 4x dx. Next 2.4.2, we have evaluated integral sin cube x dx and integral cos cube x dx, and 2.4.3 we have evaluated sin alpha x cos beta x dx, integral sin alpha x sin beta x dx, integral cos alpha x cos beta x dx. Again, try to remember all these things on your screen. Here we are going to recollect substitution methods discussed in Unit 3 and 4. Unit 3, integrand with the function and its derivatives. Unit 4, here 4.1, we have evaluated integrals for these three integrals, that is integral 1 by x squared minus a squared, integral 1 by a squared minus x squared dx, and integral 1 by x squared plus a squared. In 4.2, the same set with the only difference is in the denominator we have square root. We have three integrals of this form. 4.3 we have integral 1 by ax squared plus c plus bx plus c dx into 1 by square root of ax squared plus bx plus c dx. The difference is square root. 4.4 is important. Here in 4.3 we have in the numerator we have 1. Here we have px plus q by ax squared plus bx plus c dx, integral px plus q by square root of ax squared plus bx plus c dx. Note, in 4.4 find a and b in px plus q equal to a into d by dx of ax squared plus bx plus c plus b. And for x squared minus a squared substitution, remember the substitution x equal to a secant theta, a squared minus x squared x equal to a sin theta, and x squared plus a squared, the substitution is x equal to a tan theta. You try to remember and recollect all these formulae, or sorry, all these methods on your screen.